I will be talking about the James Webb Space Telescope. This talk is an overview. It was originally scheduled to be a hyperwall talk. So if you can imagine your computer screen is really, really big, maybe you need to just kind of zoom in close. But I'm going to be covering the Webb telescope science and then the construction that we've done up until this point, and a little bit of a look ahead. So starting with the top level overview, the James Webb Space Telescope is a 6.6 meter space telescope. It's the successor to the Hubble and Spitzer space telescopes. It's the first time that NASA will be using deployed optics in the visible to infrared region. And there are 4 instruments going from 0.6 to 28.5 microns. The observatory is passively cooled to less than 50 Kelvin, with one of the instruments actively cooled using a refrigerator to 7 Kelvin. James Webb was the second administrator of NASA. He took the agency through the Apollo era. And because of James Webb, NASA does science, because Webb took over the agency when it was human spaceflight only, and he set up the Office of Science. And so in addition to astronauts, NASA is a science agency. Webb is designed to be complementary to large telescopes on the ground, to ALMA, the Roman Space Telescope, formerly called WFIRST, and the Rubin Telescope, formerly called the LSST. It's a joint project of NASA, the European and Canadian space agencies. In all, there are 14 countries who contribute flight hardware. The lead is the Goddard Space Flight Center, where I work. The prime contractor is Northrop Grumman. Operations will be done by Space Telescope Science Institute, similar to the way Hubble is done, with the interactions to the scientific community. And our senior project scientist is Nobel laureate John Mather. I'm his deputy. So back when we were envisioning and planning the Webb telescope, the science working group defined 4 science themes to guide the construction and capabilities of the observatory. We have finding the first galaxies that formed after the Big Bang in the early universe, tracing the evolution of those galaxies over time to become the bright spiral and elliptical galaxies that we see today. The formation of stars and their planetary systems within our own galaxy, and then exoplanets and planets in our own solar system and the conditions for life. So if we look at the deepest picture that humanity has ever taken, the Hubble Ultra Deep Field, and we look for the galaxies in this picture that are the most distant or that were formed as early in the history of the universe as we can see, some of those galaxies are emitting their light. We're seeing light that was emitted less than 1 billion years after the Big Bang. And that light has traveled. And when we look at those galaxies in more detail, we see that some of them are already several 100 million years old, which means that the Hubble Ultra Deep Field does not contain the first galaxies that formed in this part of the sky. In order to see that, we need to go deeper. We need to go out into the infrared because of the redshift. If we look at what the theorists tell us, the first stars probably formed using cooling with molecular hydrogen at a redshift of 25 to 30, but the first organized galaxies formed more like redshifts of 15 to 20 when cooling with atomic hydrogen became possible. Those galaxies then started to reionize the local intergalactic medium. Those bubbles eventually joined up at about a redshift of 6. Finding the first galaxies will be a challenging observation even for Webb. We'll need very long exposures, ultra deep fields, looking for what are basically H-band dropouts. And then we'll also need spectroscopy and mid-infrared follow-up. Within our own galaxy, this is the Eagle Nebula, a star-forming region, and what we see in visible light is mostly the dusty clouds, but as we go to infrared, we can see into where the action is happening in where the stars and their planets are forming. Exoplanets, of course, are a prime topic for study by Webb, and the TRAPPIST-1 system, as we heard yesterday from Lisa Kaltenegger, is a very good target, including possibly 2 or 3 planets in the habitable zone of this star. And so following up that discovery with Webb and examining the atmospheric components of those planets, we'll be able to see things like determine whether there is liquid water on the surface and possibly some organic molecules or carbon dioxide, methane, etc., in the atmosphere. Moving on to other planets, the TESS mission has found many very good targets for Webb, including some of the brightest planets transiting some of the brightest stars in the sky. And with the apparently bright star, we get lots of signal to noise to study the atmospheric components. So TESS and JWST will work together to be a sort of an exoplanet factory. And within our own solar system, Webb cannot point at the sun, so we can't observe Mercury, Venus, and Earth. But Mars, Jupiter, and Saturn, which are very bright and saturate in some modes, there are some ways that we can study, particularly with spectroscopy, we can study those planets. But the outer solar system, Uranus, Neptune, the moons of the outer solar system planets, Kuiper belt objects, that is all prime JWST territory. Within cycle 1, the first year, there are going to be 3 types of Webb programs. There have already been selected from the community the early release science programs. That's 460 hours with 13 different programs. All of those data most of the data will be taken for these programs in the first 3 months, and all of the data will be public immediately. So this could be the first opportunity for members of the community to get their hands on JWST data, and in particular to start planning their cycle 2 observations to follow up. There's about 4,000 hours of guaranteed time observations within the first cycle, and the call for proposals for cycle 1 general observers is now open. We're offering 6,000 hours, and we're encouraging people to start early using the astronomer's proposal tools and exposure time calculator to begin planning your observations. This is a family portrait of the 4 instruments. The near-infrared camera is our main imaging camera here in the middle. Behind it is the guider and the nearest instrument, which is our Canadian contribution. The near spec is a multi-object spectrograph, the first time that we'll have flown a true multi-object spectrograph in space. It includes a MEMS-based microshutter device to get up to 100 targets at once in a 10 square arc minute field of view. And then last but not least, there's the mid-infrared instrument, which does both imaging and spectroscopy at the longer wavelengths from 5 to 28.5 microns. So how do we build a space telescope? Well, it's a very iterative process. We first start with a component, say, for example, the microshutter array, and we put it through a test, a thermal vacuum or in some cases a deployment test, see if it works. We then simulate launch using acoustic and vibration test. You can see an image of one of our mirror segments going through a vibration test. And then we take that component and we do another test, another thermal vacuum, cryo vacuum test, or deployment test to see if it still works and therefore demonstrate that it will survive launch. We then need to assemble that component into the next higher level, in the case of the microshutter array, we put it into the near spec instrument, and we repeat the testing process and assemble the near spec into the instrument compartment and then put it onto the telescope and so forth. So that's what we've been doing over about the history of the project. And here's a picture of the assembly of the primary mirror. The primary mirror is made up of 18 beryllium mirror segments, each one coated with gold, and they're assembled onto a carbon fiber backplane. And the two side wings, the two sets of 3 mirrors on the sides will be folded back for launch and will come out and be deployed after launch. So this is the assembly of the telescope, and each of the mirror segments at this point was protected by a black cover. The secondary mirror is a very interesting optical component. It's a convex mirror, and it at 65 centimeters diameter, it's almost the size of the Spitzer primary mirror. That shows you how big the Webb project is. The Webb secondary mirror is also made of beryllium coated in gold for good infrared reflectance. The mirror was assembled together at the Goddard Space Flight Center. Here are some of the people that worked on it. And this is a really nice picture where the photographer lined up the NASA logo on the back wall to be reflected in the Webb mirror. And this also shows you that this is not a flat mirror, it's a powered optic because of the distortion you see in the NASA logo. After assembling the mirror together, we installed the instrument compartment into the back side of the mirror, put them together and then we put the telescope and instruments through a cryogenic vacuum test. This was a comprehensive 3-month-long test. It was done at the Johnson Space Center in Houston in a historic vacuum chamber. This vacuum chamber is 12 meters in diameter and 35 meters high. And the vacuum chamber was originally built in the 1960s for the Apollo program. And in fact, the Apollo astronauts practiced walking in their spacesuits inside this vacuum chamber in a vacuum. The Webb project took over this chamber, took out the simulated lunar surface, installed a helium shroud to bring the temperature down to as cold as 25 Kelvin inside the chamber, and then put the Webb telescope through this 3-month-long test. During the test, we had Hurricane Harvey, which dumped 51 inches of rain onto the Houston area, but the hardware survived, the people survived, and the test was only shut down for about a day or two due to the hurricane. This is a picture that was taken from inside the chamber during the test. There are various photogrammetry cameras that will measure the position of all of the elements inside, and a bunch of those pictures were added together to make this view of the Webb telescope in a space-like environment. Meanwhile, we were assembling the spacecraft and the tennis court-sized 5-layer Kapton sun shield. This was done at the Northrop Grumman facility in Redondo Beach, California. And this is a picture of the spacecraft and sun shield going into its own thermal vacuum test at the Northrop Grumman facility. We then brought the telescope and instrument compartment out to Los Angeles area, and we installed the telescope and the sun shield and the spacecraft together. So here's a picture of that installation. The telescope's being held up by a crane and moved over to the sun shield. And here we have just before the two came together. This was done last summer. And then after attaching and assembling the telescope onto the spacecraft and onto the sun shield, we did a full deployment test of the 5-layer sun shield. So this is pretty much almost as close as we get to what Webb will look like when it's out in space. The only thing that's not deployed on this are the 2 side wings of the primary mirror and the secondary mirror, which is still folded up at the top. Just for a matter of scale, to show what a 6.5-meter mirror, space telescope mirror looks like, here's a picture of a person on a crane to show you the scale. So it's a big satellite. We've now, after that final sun shield deployment test, we've folded it all up to get it ready for the final vibration and acoustic testing, which will happen later this summer. So we're almost ready for that next milestone in the project. That will be the final vibration and acoustic testing of the fully assembled flight observatory. And then following the vibration and acoustic testing, we will then do another full deployment of the sun shield and the optics to show that vibration and acoustic testing didn't cause anything to go wrong. And that will ensure that we know that the observatory will survive the launch. So here's an overview of what we still have left to do. We've done the installation of the telescope onto the spacecraft. Complete stow to launch configuration is just about done. And the next step this summer will be to take it to the environmental test facilities, which is still out at Northrop Grumman, but in a different building. There'll be acoustic and vibe testing. Take it back to the clean room, and then the full observatory deployment again. It will then be stowed and ready to ship to the launch site. The launch site is in Kourou, French Guiana in South America. The Webb will be launched on an Ariane 5 rocket, which is part of the European contribution to the mission. And Ariane launches from Kourou. And then after launch, we'll do the final deployment in space of the sun shield and then the telescope and secondary mirror. And then we will go through the remainder of the complex 6-month commissioning process. Commissioning the telescope will take quite a while. The first month is the deployments and cooling to the point where the instruments can operate. We then spend 3 months commissioning the telescope, lining up those 18 individual mirror segments and getting them so that they will all work together and provide the optimum point spread function, not just to the NIRCam, but also across the field of view of all 4 instruments. That's an iterative process to get them all lined up. Then that will be followed by 2 months of commissioning of the science instruments, checking out each of the various modes of the instruments, and to get ready for the start of cycle 1 science, 6 months after launch. So what will we be doing in that first year? Well, a lot of that is up to you. The cycle 1 call for proposals is open, and we recommend that you get started as early as you can working on your proposals, because putting together a Webb proposal is a little bit harder than a Hubble proposal, because we're using a single stream submission. So what's called phase 1 and then phase 2 in Hubble proposals, you have to do all of that at the beginning for Webb. There's a lot of online documentation at the JWST-docs jwst.stsci.edu website. If you are looking for updates, you can sign up for the JWST Observer email list or Twitter or Facebook for updates. So we recommend that you start by becoming familiar with all of the web capabilities, terminology, and look through the documentation. Check out if your targets of interest can be observed by looking at the duplication checker and the visibility, and then start to work with the exposure time calculator. Our ETC is more complicated than a simple signal to noise calculator. It's actually more like an observation simulator, and it will help you to determine all of your observing parameters. You should also get started early with the astronomer's proposal tools, putting your observations into the APT while you are writing your science proposal text, which will be what the peer review looks like. You would submit your proposal with APT, and you can go ahead and submit as soon as you've got a draft ready, because you can continue to submit updates up to the deadline. The deadline is currently on hold, and we'll have an announcement about the deadline in mid to late July. In cycle 1, there will be 6,000 hours available. You can also write archival proposals to get funding to analyze the early release science observations, and there is also theory proposals. We recommend that you get started as early as you can. So here is a picture of a model of the JWST that was taken in 2005 with a couple of hundred of the people working on web. This is me down here. And here is a picture taken more recently of the actual observatory in the clean room. I'm not in this picture because I don't go in the clean room, but these are some of the people that did work on the web in the clean room. If you'd like to learn more about JWST, we have some resources on the website. There is a special issue of the Space Science Reviews Journal, which we published in 2006, that has a complete overview of the goals, the science goals of Webb, and the design before we started building it. We've had 3 specialized conferences since then, in 2007, 2011, and 2015. The proceedings and some of the talks from those conferences are online. We have sessions like this at the AAS meetings and SPIE meetings, and there is a conference scheduled for September in Stockholm on science with the Hubble and James Webb Space Telescopes. So there's lots of resources online to learn more about Webb. Thank you for attending, and I guess we're going to you can put your questions in the chat line.
So we have one question from Roger, who said, at what temperature was the sun shield deployment test conducted?
The sun shield deployment test is done in air at room temperature. We don't have a vacuum chamber big enough to test it in a vacuum or at the temperature of space. Of course, the sun shield deployment is done still in sunlight. So it's only after the sun shield is fully deployed that the telescope will start to cool down. But we're not able to test it in vacuum on the ground, so we had to do that in the clean room in the air.
Very good. So we have not a question, but a comment from Richard that said, perhaps it is worth noting that many observations in GTO programs will be public immediately. This plus the ERO data will make archival proposals very interesting. So that's just a comment from him.
Yep, I agree entirely. Archival proposals will be accepted for any data that's public immediately, and that includes all of the ERS and yes, some of the GTOs are also making their data public right away, and those data would be available for archival research. And if you can do research without funding, you can just get the data as soon as they're available and get started as well.
All right, we have a question from Piron. Is there a specific preparation when the JWST will arrive to French Guiana, and will it be mounted in the rocket?
Right, so we will be shipping the observatory from Los Angeles to French Guiana by boat through the Panama Canal, and it arrives about 3 months before the launch. There is a number of preparations that will be done at the launch site to install the payload into the rocket fairing, get the rocket and the rocket fairing ready to go, and that's a process that is scheduled to take about 3 months.
Okay. We have a question from Juan. Are the different parts of the telescope tested for vibrational acoustic analysis separately and then put together for a final test?
Yes, that is the process that I outlined, where each component is individually assembled and tested before it's integrated together at the next higher level. For example, the example I gave earlier in the talk was we build the microshutter array, we test it with the vibration and acoustic, then we assemble it into the near spec instrument, we test the instrument, again, vibration and acoustic testing and vacuum testing. We then assembled the near spec into the what we call the ISIM, the Integrated Science Instrument Module. We tested that, both vacuum testing and the vibration and acoustic. We assembled the ISIM onto the telescope, did more testing, and the telescope onto the sun shield. And now when it's all together in one piece, there will be a final vibration and acoustic test of the whole observatory. So yes, it's definitely an iterative process. We test everything at the component level and build it up and test it again.
All righty, we have time for one more question from, I don't want to say your name incorrectly. So how long does it take for the vacuum chamber to reach the operational vacuum for the JWST? And what is the spectral resolution of the spectronomy?
Okay, so the vacuum test, the big chamber in Houston took about a month to get to its operating temperature. It takes a lot longer to cool down to operating temperature than it actually takes to pump the air out and make it a vacuum. So the big delay, it took about a month to cool down to the operating temperature. And then there was another question, the spectral resolution of the spectrographs ranges from a resolution of 100 to resolutions of about 3,000. And all of the individual capabilities, the different modes and the spectral resolution as part of in the different modes of the different instruments and the wavelengths, you can get that from the website.